So you're writing Python. Your logic is absolutely flawless. But then you run your code on a massive dataset and it just crawls. It's frustrating, right? Well, every Python developer eventually hits this exact same wall. And when they do, they usually turn to the internet and find the ultimate age-old Stack Overflow question: why are NumPy arrays so fast? Okay, let's really dive into this today, because understanding the answer is literally the key to unlocking the true potential of scientific computing in Python. And just to be clear, we are not talking about shaving off a couple of microscopic milliseconds here. The stakes are huge. We're talking about a complete transformation of your workflow. Based on the performance benchmarks we're digging into, swapping out standard Python loops for optimized NumPy operations can give you a massive 50 to 56 times speedup. To put that into perspective for you, imagine a script that normally takes 30 agonizing minutes to run. With NumPy, that drops to just 2.5 seconds. That's the difference between walking away to grab a coffee and getting your results the second you hit enter. So welcome to this explainer. Today we are taking a deep dive into the hidden mechanics of Python's most powerful numerical engine. We're going to strip away the surface-level syntax and look at what is actually happening down in your computer's memory that makes NumPy the absolute backbone of modern data science and machine learning. All right, here is our roadmap for today. 1. The Python speed problem. 2. The power of the ndarray. 3. Vectorization and broadcasting. 4. Memory, specifically views versus copies. And finally, 5. The broader NumPy ecosystem. Let's kick things off with Section 1, the Python speed problem. Before we can really appreciate the genius of NumPy, we have to diagnose exactly why standard Python lists fail so spectacularly when you throw heavy math at them. Now, don't get me wrong, standard Python is incredibly flexible and super easy to read. You can toss integers, strings, and floats all into the exact same list without a second thought. But when you use a standard for loop to iterate through them, the CPython interpreter, which doesn't optimize compiled code ahead of time, has to do a staggering amount of work. At every single step of your loop, it has to look up the method, check the dynamic typing, and figure out, wait, am I adding an integer or a float right now? And honestly, it's that constant overhead that completely kills your execution speed. You can actually see what that looks like under the hood right here. On the left, we've got standard Python lists. They are basically arrays of pointers that point to random objects scattered all over your computer's memory. But on the right, that's the NumPy ndarray. These are densely packed, contiguous blocks of C memory. They have one unbreakable rule. Every single element must be the exact same data type. Because it's homogeneous, the CPU doesn't have to waste time checking types at every step. It just blazes through the data in one continuous swoop, using something computer scientists call locality of reference. It's incredibly efficient. Moving right along to Section 2, Power of the ndarray. Let's formally introduce the hero of our story here. Created by Travis Oliphant back in 2005, the ndarray stands for an n-dimensional array. By definition, it's a homogeneously typed array of a fixed size that acts as a strided view on memory. I know that sounds like a mouthful, but the most crucial word there is homogeneously. Because NumPy knows exactly how many bytes each number takes up, say an int 64 versus a float 32, it gets to bypass the clunky Python object model entirely. It pushes all the heavy math down into highly optimized, compiled C code. It's fast because it's completely predictable. And here's how that data is actually structured in practice. NumPy organizes these dimensions into what it calls axes. So if you're looking at a 2D matrix, axis 0 runs vertically down the columns, and axis 1 runs horizontally across the rows. This is brilliant because when you use built-in aggregation methods like .sum or .mean, you just tell NumPy which axis to compute over. Boom! You effortlessly find the average of every column or the maximum of every row, and you didn't have to write a single, slow Python loop to do it. Which brings us to Section 3, Vectorization and Broadcasting. These are the heavy-hitting techniques NumPy uses to completely eliminate those standard Python loops. Now, if there is absolutely one core concept you take away from this entire explainer, make it this: the golden rule of broadcasting. In data science, you constantly need to do math on arrays that are different shapes. NumPy lets you do this without crashing your program, but they have to obey this strict rule. When comparing dimensions, they only match if they are exactly equal, or if one of them is exactly 1. Let's play that out in a real scenario so you can see the magic. Say you want to add a 3x1 array to a 3x3 array. Step 1, NumPy right aligns their shapes in memory. Step 2, it compares them.
The rows are 3 and 3. Perfect, that's equal. The columns are 1 and 3. That also works because one of them is a 1. So step 3, NumPy virtually stretches that size 1 dimension to match the 3. But here's the crazy part. It does this stretching instantly in memory without physically duplicating any data. It uses CMID, single instruction, multiple data, CPU instructions to do the math everywhere, all at once.
All right, section 4, memory, views versus copies.
Now listen up, because even with vectorization, this is the #1 area where developers accidentally destroy their performance and completely thrash their system's RAM. You have to know when NumPy returns a view versus a copy. On the left, we have basic slicing, like grabbing every second element from index 0 to 10. That creates a view. It's lightning fast, running in O of 1 constant time, because it just creates a new header pointing to the exact same memory buffer. But look at the right. Advanced indexing. If you pass a specific list of index numbers, you force NumPy to allocate a brand new, massive array in memory and physically duplicate the data. That runs in O of n linear time. Do that on a massive dataset, and your code will absolutely grind to a halt. So, how do we avoid those memory bottlenecks? I've got a few actionable tricks for you. First off, rely on in-place operators whenever you can, like plus equals or times equals. Or use the out parameter that's built right into NumPy functions. It lets you write your results directly into a pre-allocated array, which stops the CPU from creating and tossing away temporary arrays. Oh, and definitely know your reshaping functions. The ravel function is your friend because it flattens an array by returning a shared memory view whenever possible. Flatten, on the other hand, will always force a completely new memory copy. Use it wisely.
Finally, let's wrap up with section 5, the NumPy ecosystem.
It's super important to understand where NumPy actually fits into the broader data science toolkit. Let's compare it to another absolute powerhouse, Pandas. Now, Pandas is actually built on top of NumPy, but they have very different jobs. Pandas, created by Wes McKinney, is your go-to for messy, tabular data, handling missing values and shifting rows and columns around like a giant spreadsheet. It handles massive datasets brilliantly, but is pretty memory-heavy. NumPy, on the other hand, is the undisputed king of raw numerical data. It's incredibly memory efficient and gives you the absolute best performance for heavy math on structured matrices. And you know, this whole ecosystem is constantly evolving. In fact, with the recent shift to NumPy 2.0, they've really cleaned house. They stripped out a bunch of old, cluttered aliases. For instance, you can't use np.float anymore. You have to be explicit and say np.float64. Constants got standardized too, so np.nan is now fully lowercase. But the biggest catch for developers is the C API and ABI breakage. That means any older precompiled binaries built for NumPy 1.x are going to throw an import error now. So if you're writing production code, you definitely want to update your syntax to ensure everything stays compatible. Which leaves us with a really fascinating question about the future. Traditionally, NumPy arrays live in your computer's main memory and run on a single CPU. But today, deep learning requires massive clusters of GPUs and TPUs. While NumPy is still the reigning champion of the CPU, we are seeing drop-in replacement libraries like CuPy and Google's JAX stepping up. They mimic the NumPy API perfectly, but automatically accelerate all that math on GPUs. So as our datasets get unbelievably huge, is NumPy going to natively adapt this new hardware? Or will these GPU-accelerated clones completely take over scientific computing? It is going to be an absolutely wild frontier to watch. Thanks so much for joining me on this explainer, and hey, keep exploring the data.